the way that we draw molecules out on paper is sometimes misleading about what they actually look like, how the atoms arrange themselves around each other. Okay? The way that we typically figure out what the shape of a molecule is going to be, like this guy here, is with a theory called valence shell electron pair repulsion theory, or in short, we do VSEPR theory, or VSEPR theory, sometimes people say it. Okay, so valence shell electron pair repulsion theory is a mouthful, and it seems like something that would be very, very difficult to understand, but really, it's just ideas that we've already come across, and we just put a new name on it. So, if we think about it and break it down, valence shell just means the electrons on the outside edges of the electron cloud, the ones that are available for bonding, and the ones we've already been looking at. So, we're not focused on the inner core electrons near the nucleus, we're just focused on the farthest out electrons that are available for bonding. Okay, that's cool. Okay, so check those off. VS is good. Electron pair is just talking about pairs of electrons. Electrons tend to pair up in covalent bonds when they're shared, okay, and they also tend to pair up when they're left alone on a central atom or another atom that is not using them for bonding. Typically, the electrons that are left alone and don't bond are paired up. Okay? So, check those off. Electron pairs just show up in bonds and also in lone kind of pairs of electrons when they're not being used in bonding, and non-bonding pairs of electrons. Okay? And repulsion just means repelling. It just means pushing things apart. So when we have electrons near each other, they're going to repel each other. Negative charge and negative charge repel. So if we're dealing with electron pairs in the valence shells of atoms, like in the atoms that bond together, okay, or the electron pairs that sit on a central atom that don't bond, they need to have their space, or they're going to repel each other, okay? And they do. So the best way to get a good idea of what shape your molecule should have is to take that into account, to say that all your things that have electron clouds, okay, or all your places where you have spare electrons are going to need to have room. And so they're going to push away and repel each other, okay? So VSEPR theory helps us predict what a molecule is going to look like based on that. So we're essentially counting two things around a central atom to figure out how the atoms arrange themselves around that kind of central piece. We count bonded atoms. We also count lone pairs. Now, if you have models like this, or like this, okay, or you have some great computer programs like MoleView, or your brain is very good at visualizing three-dimensional things, then you might be able to just imagine how things will push apart from each other and say, I can see the picture of the molecule in my mind. But not everyone can. And also sometimes we don't want to use up all our brain space on trying to move around atoms and electron clouds in our minds. So the more surefire way to figure out what a molecule is going to look like is to use the axe method. Okay, this is going to give us something from VSEPR theory based on how many atoms there are bonded to the central atom, okay, or how many lone pairs of electrons are left on the central atom. We're not going to worry about lone pairs on outer surrounding atoms because that would help dictate what shape those atoms would have, kind of with the stuff around them. We care about the one thing in the center. With bigger molecules, that might be, something that we'd worry about. But for now, we're just going to stick with looking at the central atom in the middle. Okay? So, I'm going to get this out of the way. Move this down here. So the axe method basically just counts up things that make a molecule, like a central atom. So we use A for the central atom. Okay? How many atoms you have bonded to that central atom? We use an X to signify that. And then for our lone pairs of electrons, we use an E to count for those. So on my drawings up here, A is representing the central atom. X is representing bonded atoms, okay, that are covalently bonded to that central atom. Okay? And we're going to have lone pairs represented by these little cards that we'll come back to here in a bit. These are going to be how we count our E's. Okay? But we're going to first look at some examples where we're only bonding atoms together. Okay, so for instance, if we just take one central atom and bond one atom to it, something like this, okay, that central atom only has one electron domain around it. Okay, a bonded atom or a lone pair counts as an electron domain. Okay, so in total, just one electron domain from one bonded atom. If we wanted to write the AX code for this, okay, A, again, stands for the central atom. That part never changes. It's always just going to be an A. X stands for your number of bonded atoms. Okay, so we have one of those. So kind of like how we'd write a chemical formula, we put a little 1 down there to say there is one bonded atom, so X1. Okay, and then E0 is used to signify we have no lone pairs on this. We don't have any extra pairs of electrons hanging around on our central atom, that A, and taking up space. Okay. Based on this, we can have the shape of the molecule designated as whatever this ends up looking like. So if you go and look up the AX code, AX1E0, then you should come up with the molecular shape linear. You might also see it called the molecular geometry. The same thing, it just depends on if you want to sound fancy and say geometry, or if you just want to cut to the chase and say shape. Okay? So this is about as simple as it gets. We don't really have any other options here. You just bond one atom, done. Okay? Now you might also see this kind of cut out. Okay? You might have an AX code that leaves out the E because it's like, oh, if it's E0, then why are you writing the E? Kind of like a chemical formula. If a compound does not contain chlorine, we don't write Cl0 next to it. So depending on what chart you're looking at, you might not see the E written at all if you have no extra electron pairs. Okay? You might also not see the 1 written for things like this, where you just have one X or one E. And they just say, oh, it's like a chemical formula. You don't write, Na1Cl1 or H2O1. You just write, H2O or NaCl. So you might see your AX code something like this, just AX. I like to show everything. So I'm going to put it back. So that way I'm showing I'm explicitly counting everything that's there and not there. Okay. Well, what if we step it up to something with 2 electron domains? Something like this guy right here. Okay. Well, I've got a central atom A, and I've got 2 bonded atoms, X and X. So my AX code could be AX2E0. Okay. A molecule like that might look like this. Okay. We've got these two kind of coming out, as far apart as they can get from each other. There's about 180 degrees between these two, and we can't really get them any farther apart. Okay? We would call this a linear shape, okay? Just like we called this one linear. Now, they are different looking molecules, so sometimes you'll come across shapes that are the same word, but, mean, kind of go along with a different AX code. So, like, this might be like your AX here. This might be your AX2 here. So they both end up being called linear, but 2 different molecules. So just because something says linear, don't feel like, it's got to be just, this one. It might be something like this. Okay, we can arrive at the same molecular shape with different kind of combinations of bonded atoms and also electron pairs, which we'll see later in a bit. Okay, so either case, the electron domains, okay, really only allow us to have atoms in a straight line for these two. Okay? Even if I had one of these bonded atoms actually is just an extra kind of lone pair hanging around, and we're not actually bonding to something. I cover this up here. Okay? That would give me this code right here. AX1E1. We still call it linear because this is just in a line. And in fact, if I switch this over here, it looks almost exactly like this guy with 1 electron domain. But there are still 2 electron domains. That's a key thing. Okay? we have a difference between what we call the molecular shape and the electron geometry. Okay, so the electron geometry deals with where we have bonded atoms and lone pairs of electrons. The molecular shape cuts out the extra electron pairs that aren't being used for bonding. So in this case, we happen to get the same name for both these options, whether I have both bonded atoms as my two electron domains, or if one of those electron domains is a lone pair of electrons. I still get something I call linear. But for other examples, like the one we're going to get to next, it can change a little bit. Okay. So let's move on to this next example, where we have 3 electron domains. Okay. If we consider having all of them be bonded atoms, XX and X, we could call that AX code AX3E0, or just AX3, right? Which we would call a trigonal planar electron geometry, meaning whether you have bonded atoms or some combination of atoms and lone pairs of electrons, you're going to get something that lays flat like this. So they're all in a line, okay, and they make a triangle shape, where each one of these cotton balls is representing an electron domain, and your center would be in here somewhere, and there, through the middle. So if you've got the full picture, we call that trigonal planar, okay? And that is the electron geometry as long as you have 3 electron domains, okay? So if all 3 of those are bonded atoms, the molecular shape is also called trigonal planar. But what if one of these bonded atoms is not an atom, and it's just a lone pair of electrons kind of taking up that space? Well, then it's not really going to look like a triangle anymore. Let's try it. Scoot this in here, just like that. Okay, well now, the only part of the molecule that I see, or rather that we have with matter there, and not just electrons zipping around, is right here. Okay, and even better, it might be easier to see it like this. Okay, this is what we call the bent shape, or at least this is one version of a bent shape, because it looks like the molecule is bent down. Okay? Now, if you saw the formula for this chemical, it would just be one central atom and 2 atoms bonded to it. So you may be swayed at first to say, well, that's going to be linear because there's just 2 atoms, they're going to be in a straight line. But this lone pair of electrons makes a big difference. It's another electron domain. Okay? So we still end up with a total of 3 electron domains. The electron geometry for this is still trigonal planar. But the shape of the molecule itself is what we now change. We now call that bent, and our AX code matches it, AX2E1. So, let's see. This was the shape of my molecule to start with, okay? But one of these is not actually a bonded atom. It's a lone pair of electrons. What I'm left with is this bent shape here, okay? All right. What if we had another lone pair of electrons on there? Grab another one. Cover this right there. Okay. Well, now what's left is we have the bent. We took away another bonded atom. Now it's just linear, kind of like this first one that we started with. So we kind of cut away from the whole picture, the electron geometry, to get the molecular shape. But we still have to consider where the bonded atoms wind up because of the lone pairs of electrons. Okay? We get the molecular shape because of the electron geometry. Okay? And we cannot forget about that. Do not jump to the conclusion of being like, I'm just going to count the atoms and then they just spread out as much as they can. Okay? You got to watch out for those lone pairs of electrons. Okay. So, with 2 lone pairs of electrons, we are getting this molecular shape here, AX1E2, or again, you might just see that as AXE2. That would also be fine. Okay? And we would also call that linear. yet again, another version of linear that comes from a different number of total electron domains. Okay, and again, we call it that because we end up with everything in a straight line. Okay, well, let's get to something a little bit trickier. Okay, once we get 4 electron domains, we can't really get things to sit next to each other in a plane, in kind of all in a straight line with each other, okay, on a flat surface. We start to get into molecules that need a little bit more room, okay? When we have, you can't see me. When we have 4 electron domains, that electron geometry is called tetrahedral. Okay, tetra for 4, hedral for shape, shapes, right? Okay, so we've got 4 points on this shape here. Okay, this is a tetrahedron. Okay, and these would signify where our electron domains are. These cotton balls are where our electron domains are. So the center of our the central atom would be somewhere in here, kind of in between these. Right? So the full picture of this, the tetrahedral shape, okay, also goes along with having 4 bonded atoms. Okay, AX4E0 has the molecular shape tetrahedral, just the same as the name for the electron geometry with 4 electron domains. Okay, it looks something like this. Okay, if we go and swap one of these out for a lone pair of electrons, so we would have 3 bonded atoms and 1 pair of electrons. Let's see. Something like that. Okay, you may first look at that and be like, trigonal planar. But not quite, because again, we're starting from this shape. Okay, if I remove one of these atoms here, these aren't all in a line. They're not all flat with each other. So this isn't in a plane. They would have to be like that to be trigonal planar. But they're not. They're like this, kind of crooked of each other. Okay? So this is a different molecular shape. It's not trigonal planar. Right? The way that we try to help show that on paper is with bonds like these. Okay? When we show, I'm going to move this for a second. When we show a dashed line like this, or a fat wedged line like this, we're trying to show depth to our drawing. So a wedge like this means that the bond is coming out at you. Okay, so this one is like, coming out like this. Whereas this one, the dashed one, is saying it's going out behind whatever you're drawing on. So it could be a piece of paper, could be a laptop screen, could be a whiteboard, but it's going away from you. So if I could stick my hand through the board, it would be going that way, and that way specifically. That way. Okay, so this is supposed to show this is going away from you, this is coming towards you. Again, to try and give it some more 3D depth. So if you drew it as a shape, it might be like something like that. The line back there. You got like an X there, an X there, X there, X there. Something like that. You got some shading on there, and you can do a whole art lesson about it. Okay. So these are no different than any other single bond. It's just another way of showing some depth to this, to give it a little bit more of a 3D picture. So I'm going to cover up one of those. I'm going to cover up the wedge. Okay, but do not be fooled. This is not trigonal planar. Okay, this is a new shape. It has the ax code AX3E1. Okay, and we call it Trigonal Pyramid or Trigonal Pyramidal. So you have 3 points at the bottom of your pyramid that kind of lead up to your central atom, like that. So we call it trigonal pyramid. Or again, if you're describing it, trigonal pyramidal or pyramidal. I always miss those that. I think it's pyramidal. Trigonal pyramidal. What happens if you throw in another lone pair of electrons? Well, we swap out another X for an E. we go from having AX3E1 to AX2E2. All right. So our electron geometry is still tetrahedral, but we now are down to 2 bonded atoms. And look what we got again. We got bent, like this shape. So this is our bent shape. Just kind of crooked. Okay, so again, only 2 bonded atoms, but they're not linear. They're not in a straight line. Okay, because we've got 2 lone pairs of electrons hanging out on these other sides here of the atom that have to repel and push those bonded atoms out of the way. Okay, so this is the bent shape. Okay, now there are 2 more sets we're going to look at. Okay, molecules with 5 electron domains and molecules with 6 electron domains. So I'm going to move my laptop here and then we'll continue on. Okay, this one can be kind of a doozy. 5 electron domains. Okay, so when we have all bonded atoms, we get something like this. Okay, and the electron geometry has a shape called Trigonal Bipyramidal. Ooh, I caught myself on that one. Or we call it a Trigonal Bipyramid shape. Okay, so we've got, it's like a trigonal pyramid, except we have one coming up on top and one on bottom there. Okay, so it's like 2 pyramids stacked base to base. We have 2 pyramids there, and there's the triangle at the center. Okay, so that's our electron geometry for 5 electron domains. Again, where these balls are electron domains there. It might be a little bit easier to visualize with one of these guys. So we have 2 on top and bottom, and then 3 kind of around the center there. This one's kind of interesting because we have these 2 guys at top and bottom that are 180 degrees apart from each other and 90 degrees apart from these guys here in the middle. Okay, and these guys in the middle are 120 degrees apart from each other. Okay, so our first shape is just all of these bonded atoms, okay, which is AX5E0 or just AX5. We still call that a trigonal bipyramid or trigonal bipyramidal. Right? If we go and replace those with a lone pair of electrons, cover that one. Okay, it's kind of hard to see, but what we're left with is still the 2 on top and bottom. And we've got 2 of these kind of hanging around the middle. Okay, so we go from having this to this right here. Okay, we call this the seesaw shape. Wow, seesaw shape. It's the seesaw shape. So if you think of this as kind of like the feet of the seesaw, and these are kind of like where you'd sit. Oh, drop it. It's okay, these things are durable. If you think of it kind of rocking on these 2 atoms like feet, and then it goes and kind of goes back and forth like that. It's like a seesaw, you know? So this is the seesaw shape. Okay. AX4E1 is its ax coder, just AX4E. If we throw in another lone pair of electrons instead of a bonded atom, okay, we get a T-shaped molecule. All right. Again, we take away one of these from the middle. What we wind up with is something like this. Okay. Cool. Now, you may be wondering, how do I know which atom to remove? Like, why isn't it one of the top or bottom ones? Why is it one of these kind of ones in the ring around the center? Well, here's a secret we don't really talk about much. These lone pairs of electrons actually take up a little bit more room than a bonded atom. Since they're not localized to like make a bond with a specific atom, they can kind of stretch out a little bit more. So as a result, we want to put those lone pairs of electrons where they have the most room. Well, if these atoms in the middle usually have 120 degrees between each other, we probably want to give them that extra bit of room rather than putting them up here where they're 90 degrees away from other atoms. So it gives them a little bit more space to stretch out. Okay, so that's how we get the T-shape. Okay, AX3E2 is T-shaped. Let's throw in one more lone pair of electrons. Something like that. Okay. Now all we're left with is these two bonded atoms, and that's a linear shape. Okay. Now just having two bonded atoms left is not always linear, but since we've been taking away from this kind of ring around the center, once we remove this last one, all we have left is two atoms in a line. Okay. So this is a linear shape. All right. So those are our different shapes for our 5 electron domains. One left. All right, let's talk about 6 electron domains. Okay, when we have 6 electron domains, our electron geometry is called octahedral. Again, no matter whether you have all 6 of those be bonded atoms or some of them lone pairs, your electron geometry is octahedral. We call it octahedral because, oh, wait, hold on, 1, 2, 3, 4, 5, 6. You'd think it would be something with 6, right? Because I mean, like we did tetrahedral is 4. Why isn't this like hexahedral or something like that? Why we got 6 things here? Well, the reason is when you make it a shape like this, you've got one side, one side, one side, one side, and then you've got the same on bottom. So you've got 4 sides on top and 4 sides on bottom. That makes 8 sides, excuse me, in total. So we use the prefix octa for that. So octahedral means 8 sides. And I might have to go check, the origins of the words, but I should probably back myself up and say this is probably tetrahedral for having 4 sides, not 4 points. So I'm going to catch myself there in case anyone was about to fact check me or something. I'm going to guess it's from having 4 sides. So this guy has 8 sides, okay? Now, we don't really have sides on a molecule, but if you were to connect all the points of the electron domains, that's the shape you get. So we went with octahedral, okay? It's something like this. Okay? As a molecule, you have all 6 of these be bonded atoms. AX6E0, or just ASX6, would be octahedral also. Its molecular shape is the same as the electron geometry. So you get something like this, where you've got 4 atoms around the center. Okay? The nice thing with this one is no matter which way you turn it, you've still got 90 degrees between everything. You got 90 degrees in between these two, and you rotate it, and you got 90 degrees between these two. And if you rotate it this way, you got 90 degrees here, and 90 degrees here, and no matter where you go, it's going to be 90 degrees apart, which is pretty neat. That's about as far apart as they can go when you got so many things packed around the central atom. Now, if you throw on a lone pair of electrons, something like that, okay, it doesn't really matter where you take it away from because, they're all the same distance apart from each other. So this would be our first one. Typically, we like to turn it over like this, so the shape is a little bit easier to understand. Let me actually do that. Let me put it down here first and redraw that line. Okay, so AX5E1, or just AX5E, is what we call square pyramid or square pyramidal. Okay, because you end up with a square on the bottom that kind of goes up to this top atom, which is like to say it's a pyramid. So square pyramid or square pyramidal is what we call this. Okay, so that's our shape for AX5E1 if we have one lone pair of electrons in there. Okay. If we throw in another lone pair of electrons, this time it does matter where we put them. We can't just kind of throw them anywhere. We're very specific about this one. because we like to put them on opposite sides. Okay, again, your lone pairs of electrons take up a little bit more room than the bonded atoms do. So we want to get them as far apart from each other as we can. So we put the lone pairs of electrons on opposite sides of each other, and we make something like this, AX4E2, 2 lone pairs of electrons and 4 bonded atoms. So what we're left with is something like this, where all these atoms are in a line in the same plane. Okay, so we call this square planar, which makes for a really cool looking molecule. I like this one. Okay, so our lone pairs of electrons are here and down on bottom. We call this guy square planar. Okay, and that's the last of our options. Okay, so whenever you make a molecule, draw it out, figure out how many bonded atoms it has and how many lone pairs of electrons it has. The total electron domains tells you the electron geometry, okay, the entire kind of shape of where all your electrons domains are at. And then to figure out the molecular shape, we start cutting away wherever we have lone pairs of electrons to see just where the atoms are arranged around the center atom. So we start with kind of the base of the electron geometry, and then the molecular geometry can kind of streamline it a little bit to get a more specific shape where only the atoms are at.